Okay, let's get right into it. Welcome to today's explainer, where we're going to zoom way, way down into the fundamental building blocks of our entire universe. Whether you're reviewing for a big exam or you're just genuinely fascinated by how the world works, we are going to break down the microscopic mysteries of matter step by step. So, let's kick things off with a little puzzle. Think about this. What do you, a living, breathing human being, and a totally non-living brick house actually have in common? I mean, at first glance, absolutely nothing, right? But if we zoom in close enough, we'd actually see that both are built the exact same way at the microscopic level. It's kind of mind-blowing. Just like a house is painstakingly built out of individual bricks, and your biological body is constructed from trillions of tiny living cells, literally all matter in the universe is ultimately made up of tiny, invisible units called atoms. The atom is the ultimate building block of everything. Okay, so here's our roadmap for today's explainer. We're going to cover the quest for the atom, the evolution of atomic models, exploring the subatomic world, atomic mass and isotopes, and we'll wrap it all up with some final exam review quizzes. Section 1. The quest for the atom. It's pretty fascinating to realize that the whole concept of the atom was actually born completely from human imagination, centuries before it ever became hard science. Way back in ancient India, a thinker named Acharya Kannada suggested that if you just kept dividing matter over and over, you'd eventually hit a piece that simply couldn't be divided anymore. He called those indivisible pieces parmenus. And around the exact same time, ancient Greek philosophers Leucippus and Democritus had the very same idea, calling them atomos, which literally just means indivisible. But, it was really just a philosophical idea until 1808 when John Dalton stepped up and gave us the first scientific atomic theory based on real experiments. Section 2. Evolution of atomic models. Now, while Dalton's theory was totally groundbreaking, scientists soon ran into a major plot twist. Dalton's supposedly indivisible atom? Yeah, it wasn't indivisible at all. It had to be made of even smaller parts. So Thomson had just discovered these tiny, negatively charged particles called electrons. But since atoms are neutral overall, he had to figure out where the positive charge was hiding. So he used a really brilliant everyday analogy. A watermelon. Or, a plum pudding if you prefer. He suggested the red, fleshy pulp of the watermelon is this massive sphere of positive charge, and the negative electrons are just scattered throughout it, kind of like seeds. But of course, science never just settles. The atomic model kept evolving chronologically. We started with Dalton's solid, indivisible sphere, moved to Thomson's watermelon, then Ernest Rutherford discovered there was actually a dense central nucleus, and finally, Niels Bohr refined the whole thing by adding specific energy levels. It's this incredibly beautiful progression of scientific discovery. Let's actually look a bit closer at Niels Bohr's contribution, because he solved a massive physics headache. He figured out that electrons don't just fly around randomly all over the place. Nope, they follow fixed circular paths called stationary states, or shells. And he named these shells K, L, M, and N, starting from the one closest to the nucleus and moving outward. All right, time for a quick knowledge check. I really want you to pause and ponder this for a second. We know negative electrons are intensely attracted to the positive protons sitting in the center of the atom. So, why don't the electrons just get pulled right in and crash into the nucleus? It's a super common misconception, actually. Well, the crucial point here is this. According to Bohr, electrons revolve only in those allowed fixed stationary states we just talked about. And as long as an electron stays rigidly inside its designated orbit, it doesn't lose any energy at all. Because its energy stays completely stable, it simply doesn't spiral inwards to crash into the center. Problem solved. Section 3. Exploring the subatomic world. We've talked a lot about the overall structure, but let's officially meet the three main characters that actually live inside the atom. There are three subatomic particles you absolutely need to lock into your memory. First, the electrons. They are negatively charged, hang out in the outer orbits, and were discovered by J.J. Thomson. Then we have the protons. Those are positive, they live right in the dense nucleus, and we credit Rutherford for them. And finally, the quiet ones, the neutrons. They carry a neutral charge, meaning no charge at all. They also live in the nucleus right next to the protons, and they were discovered by James Chadwick. Now, understanding the difference between these next two terms is absolutely foundational for your exams. Atomic number versus mass number. The atomic number is basically the atom's ID badge. It is exactly the number of protons in the nucleus. Simple enough, right? But the mass number is the total weight of all the heavy stuff. So that's the total number of protons plus the neutrons combined. Section 4. Atomic mass and isotopes. So what happens when atoms of the exact same element decide to change their weight? It creates a bit of a naming puzzle, but here's a super easy trick to tell them apart without ever getting confused. Think of isotopes as twins. The word isotope has a P in it, which stands for the same number of protons. That means they have the same atomic number, they're the exact same element, but one is just a little heavier. Isobars, on the other hand, are the exact opposite. The word isobar has an A in it, which stands for the same atomic mass number, so they are entirely different elements with different atomic numbers, but they just so happen to weigh the exact same on the scale. Keep those letters straight and you'll nail it. Section 5. Final exam review quizzes. Let's see how much you've retained. We have covered a tremendous amount of ground today, so let's lock in everything we've learned with some high-yield practice questions straight from your chapter's review section. Question 1. Think back to Rutherford shooting alpha particles at that super thin sheet of gold foil. We know most particles went straight through, but what did it mean when a tiny fraction of them bounced right back at huge dramatic angles? Well, the correct answer is that those rare dramatic deflections prove the atom isn't a mushy watermelon at all. While most of the atom is literally just empty space, which is exactly why most particles passed right through, the ones that bounce back hit something incredibly dense and positively charged. Basically, Rutherford proved the existence of the tiny, hard, central nucleus. Moving on to a classic exam calculation where we need to apply the math we just learned. Let's say an atom has 79 protons and we know its total mass number is 197. How many neutrons are sitting inside that nucleus? The answer is exactly 118 neutrons. Remember that formula we went over earlier? Mass number equals protons plus neutrons. So you just take the total mass of 197, subtract the 79 protons, and boom, you are left with exactly 118 neutrons. It's simple, it's direct, and it's a super easy win for you on test day. And we are at the finish line. Here's a rapid-fire look at your ultimate revision notes covering the absolute most important takeaways from this explainer. Remember, atoms build literally everything. They're made of electrons, protons, and neutrons. Our understanding evolved chronologically from Thomson to Rutherford and then to Bohr. Oh, and here's a bonus exam tip for you. An atom's combining capacity is called its valency. Definitely keep that in mind for your chemistry tests. And finally, isotopes are identical elements that just carry a little extra weight. We've zoomed incredibly fast from comparing a brick house all the way down into the invisible, lightning-fast orbits of electrons. But you know, science never sleeps. We're continually discovering more and more about quantum mechanics and particle physics. So I'm going to leave you with this provocative question to ponder. Given how much our atomic models have changed over just the last century alone, is it ever going to be possible to completely understand absolutely everything that happens inside an atom? Keep questioning, keep learning, and I'll catch you in the next explainer.